So I'd like to welcome you all to SLAC. My name is Lance Dixon, and I'd like to thank you all for coming out this evening. And we have a good show in store for you. How many of you knew that last Friday was Particle Accelerator Day? Well, to be fair, it was only in the state of Illinois, but nevertheless, we were all dancing in the halls. I don't know about you. So, our governor, he's pretty fearless, and he wasn't about to be outdone by a wimpy governor from Illinois. So he made this Extra Dimensions Week. So as our tour guide, as we discover all about extra dimensions and what they have to do with particle accelerators, we have JoAnne Hewett. And we're very fortunate because she's A, from SLAC, and B, one of the world's experts in the field. She took her first physics class as a sophomore in college and was immediately hooked. And she embarked on a career of performing esoteric theoretical calculations, none of which she will describe here in any detail. And her research probes the fundamental nature of space, matter, and energy. She most enjoys devising experimental tests for preposterous theoretical models. And she is eagerly awaiting, as she's going to explain in this talk, the next round of particle accelerator experiments to see which of these preposterous theories might be true. After obtaining her doctorate, JoAnne held positions at the University of Wisconsin and at Argonne National Lab. In 1994, she thawed out and moved to SLAC, where she is now an associate professor of theoretical physics. She's currently the author of over 100 scientific papers, and she serves on an important panel charting the future of the U.S. high-energy physics program. Would you please welcome JoAnne Hewett as she explains Space, the Hunt for Hidden Dimensions.
Thank you very much for coming here tonight. Let's see if I can navigate the minefield of these buttons. Yes, okay. Thank you for coming and for your interest in science and extra dimensions. So, at the beginning of human civilization, men and women would crawl out of their caves at night and stare up at the sky, look at the stars in the Milky Way, and they'd ask questions. And they had some very basic questions to ask. What is the world made of? What holds the world together? Where did we come from? Very basic questions that all of humankind had. Since these early days, we've had a lot of ideas, a lot of theories, some wrong, some right. We've a lot of experiments, a lot of data. We've gained a lot of knowledge, and from that knowledge, we've evolved in our thinking. And with this evolution in our thinking, we have a set of basic questions, which are basically the same. What's the world made of? What holds it together? And where did we come from? Except the way we go about answering these questions is what's different. We actually have a refined set of questions which really address these basic ideas in a much more specific way. So there was this big panel that was organized, and they made up with the top 9, not 10, but 9, most urgent and pressing questions in particle physics today. And look what made number 3 on the list. Oh, I can't do this with my left hand. Okay. Number 3 on the list is, are there extra dimensions of space? This is a big question for us physicists, and we want to know the answer. Now, extra dimensions is something that most everybody is kind of familiar with because there's been a lot of movies and TV shows and books and et cetera which addressed it. In fact, the doctor here is coming out of his TARDIS, which stands for time and relative dimensions in space. And it was an awful lot bigger inside than it was outside, and that was the big mystery. But what we're doing today is not science fiction, but real science. We're very, very serious about the possible existence of extra dimensions, and we're very serious about how we go about in searching for them through experiment. And I'm going to spend the rest of the hour tonight trying to convince you the motivation for extra dimensions, how we think about them, and then tell you how we go about looking for them, and let you know how well we've done so far. I'll tell you the big secret right away. We haven't found him yet. But first, we need to start at a very basic, fundamental point. There's something we really need to define, because it's a concept that we all have to have together in our heads. Before we can think about extra dimensions, we have to know what is a dimension. And this is actually a surprisingly difficult concept, even though it's something we experience every day. So I'm going to try and define this in a couple of different ways. The first way is by an analogy. And the analogy is going to be traveling by a car. So what is a one-dimensional space if you're traveling in a car? Well, it's a highway that goes straight, and it's just one highway. You can only go back and forth on this highway. You can't turn north. You can only go east or west. Looking through the atlas last night, trying to find a good place in the United States that manifested this, it just turned out that Republican City, Nebraska, worked out. So if you're in Republican City and you want to leave, you have to either move to the right or move to the left. You can't move north or south to get out of Republican City, Nebraska. Highway 136 is all there is. So this is an example of a single dimension. There's only one way to go. Okay? So what's an example of two dimensions would be a city grid. So this is just a map of downtown San Francisco. Here we've got Nob Hill and Chinatown. And you see that you can either go this way on a street, or you can go this way on the street. Now the peninsula doesn't stick straight up north, so it's not quite north-south and east-west, but it's along the direction of the peninsula direction. But you can go this way, or in a perpendicular direction, this way. Okay, so up and down, or north and south, east and west. But if you're driving around San Francisco, something you're very much aware of is that there's another dimension, up, okay? There's up and there's down, okay? And so these are what we mean by the three different dimensions. We look at this red car here in the middle of Lombard Street. It has a particular point in the city of San Francisco. It's a particular point in this direction, right and left, a particular point in this direction, back and forth, and a particular point up and down. Okay? And that's how you would describe its position on that street. Well, this is just like what we do in math and science, only we have a more abstract way of thinking about it. We have a coordinate system. So it's a more abstract view, but it's the same type of thing. And here I'm going to use a guinea pig in the audience to help me describe this. Okay, so let's look at a one-dimensional space. So here's our line, okay, our Highway 136 going through Nebraska. But let's think of this as one of the rows here in the auditorium. Okay, so if we look at, just pick one of these rows at random, somebody I can shoot a laser pointer at and not hit them in the eye, okay? I'm going to pick on this gentleman here because I can reach his arm if he doesn't move. And I don't get the pedestrian. I'll have to put the safety card back up if I go shooting this laser pointer in the audience. Okay, this gentleman here is sitting at the edge of a row. Okay, so that defines his position along the one dimension of this row in the audience. If we want to further define his position, we can add an extra dimension, one that is perpendicular to the first dimension, and then any point in this two-dimensional plane is described by two numbers. So for this gentleman in the audience, he is described by the fact that he's sitting at the end of the row, and he's in the 1, 2, 3, 4th row up from the front. Okay? A three-dimensional space where you add a third dimension perpendicular to the first two, and any point in space can then be defined by three numbers. Okay? So this gentleman, again, is at the end of the row. He's the 4th row up, and he's sitting about 4 feet taller than the front of the auditorium. This defines his position in the auditorium, and it takes all three numbers, all three directions or dimensions to define this position. Now, if we tried to do a 4th dimension here and stick it perpendicular to the other three, a 4th spatial dimension, that's a little difficult for us to visualize, so we'll get to that later on. But in our everyday experience, space, as we observe it, has three dimensions. And a point in space, its location is defined by 3 different numbers corresponding to a direction, a value in each direction. Okay, so we all owe all of this to Mr. Descartes. He's the one that first came up with this coordinate system, and it's called Cartesian coordinates after him. And he did this basically 400 years ago now, a little less than that, and it stuck with us all this time, and we'll see why in a couple of slides. But here, again, we reiterate that points in the 3-dimensional space are represented mathematically by their coordinates x, y, and z. So this is our coordinate system. Now, historically, countries used to honor their famous and great mathematicians and scientists by putting them on the money. Okay, that's always nice. Today in modern society, we have a slightly different standard. As I found when searching the web, you can get a Descartes Stadium Cup. It's only about $10, and you can have it mailed to your house. And I bet the person sitting next to you at the football game won't know who that is. Okay, so the reason why this particular set of coordinate systems has really stuck around is because of its connection that it makes between algebra and geometry. It's a very simple connection between algebra and geometry, in that geometric shapes can be described by algebraic equations. So if you have a 2-dimensional plane, and you draw a circle on it, okay, you can describe geometrically the circle by the sum of the squares of the 2 coordinates in that 2-dimensional plane. Likewise, if you have a 3-dimensional sphere, you can describe this shape by the sum of the squares of each of the 3 coordinates, 1 coordinate corresponding to each dimension. So if you had a 4-dimensional hypersphere, you would describe its shape by the sum of the 4 coordinates, the sum of the squares of the 4 coordinates, each 1 coordinate for each dimension. This was a really, really big step forward in early 1600s. And it really relates algebra and geometry in a simple way, something that I'm sure none of us really appreciated in high school when we were in algebra and geometry. So fast forward to the early 20th century, and we have Einstein, who realized that there really is a 4th dimension. And he came about this when he invented his theory of special relativity in 1905, and that it's required by relativity to be a dimension at the same level as the space coordinates, which we call x, y, and z. And it's required to specify the location of event. So let's think about this for a minute. This gentleman, same gentleman, my guinea pig tonight, is sitting at the end of this row. It's the 4th row up. It's 4 feet taller than me, and he's here at about 7:44. I mean, it could be that he gets fed up with me and he leaves in 5 minutes, and therefore, if I described him by the coordinate of that chair, that wouldn't be very relevant, would it? Okay? So the time of an event is just as important as the space of an event in terms of describing when and where the event happened. Space and time are thus very much intertwined, and that's explained in sort of this is a formula that physicists would use that I had fun putting on this blackboard, because this is a website where you can take what Einstein really wrote on this blackboard, erase it, and put in anything you want. And playing with this website really delayed the progress in writing this lecture. It's really a lot of fun. Okay. But anyway, the point of looking at this is to see that space and time are really intertwined and intimately related to each other. Now, Einstein, of course, is a very famous fellow. And so instead of having a stadium cup, he has a special commemorative beer stein, which costs $150 only. Get yours now. And there's only 3,000 of them in the world, so you really do have to act fast. Okay, so this interrelation between space and time was really brought home by Mr. Minkowski, who I think first coined the word space-time. At least that's what Wiki says. Okay? So space-time is really the description of our world, which is four-dimensional. 3 spatial dimensions in 1 time, but we need to think of our world as four-dimensional. And there's a fundamental constant called c, which relates measurements of space to measurements of time. C is a speed, it's a velocity, and it's the speed of light, and it's basically 670 million miles per hour. It's pretty fast. Now, back in the early 1900s, I found out also while preparing this talk, I learned a lot, that science apparently influenced art. And the fact that the forthcoming of special relativity and the thinking of time as a 4th dimension supposedly inspired Cubism. Okay? Don't know if I believe that, but anyway, this is supposed to be a very good example of this. This is the famous painting, Nude Descending a Staircase by Marcel Duchamp. And this is supposed to depict the time motion of a figure. And this is one of the first times that a time motion of a person was painted. Usually all paintings were static before then, but this is the time motion of a person. So this is a painting of the new 4th dimension. Gosh, we just added a 4th dimension, so people started wondering, should we start adding some more? So in 1914, Mr. Gunnar Nordström showed that you could unify gravity and electromagnetism in a single theory. Now, gravity and electromagnetism were the only forces people knew about in 1914. That's the interactions that they thought described the universe. And they thought it would be awfully nice to unify them in a single theory. And Nordström showed that you could do it if you had 5 dimensions, not 4, but 5. You added 1 more dimension. Problem is, Nordström had his own theory of gravity, and he competed with Einstein's at the time. And so Einstein kind of ignored his theory. And, well, everybody ignored his theory, actually, and he was kind of forgotten about. However, 5 years later, Theodore Kaluza came up with another theory that showed that gravity and electromagnetism could be unified in a single theory with 5 dimensions, only this time he used Einstein's theory of gravity. Einstein's response was completely different. This time, oh wow, this is great, he said. At first glance, I like your idea tremendously, and this time it really caught on. However, people had a different way of thinking about the 5th dimension. These guys, Nordström, Kaluza, and Einstein, all assumed that the 5th dimension wasn't real. Why did they think that? You can't see it. Why should something you can't see be real? So they were just using it as a mathematical trick, as a way with playing with the equations such that you could unify these 2 forces. And right now, if you don't take anything else away from this lecture tonight, anytime some physicist tells you that something's not real because they can't see it, don't listen. It's worth recalling that at the same time period, some people didn't believe in the atom because we couldn't see it. Okay, so Oscar Klein, 7 years later, in 1926, was the first to think that the 5th dimension could actually be real, and not just a trick in a mathematical equation, but that indeed a 5th dimension could actually exist. If he wanted to unify gravity with electromagnetism, he had a theory, and he could sit down and calculate how big or how small this extra dimension had to be, and this was his answer. I forget how many zeros it is. I think it's like 23, 24, or something like that, but it's pretty small, pretty small. Einstein really liked this idea, though, used his theory of gravity. Said the paper was beautiful and impressive. So now I need to back up a minute and talk about unification of the forces. Because what we've learned from the past few slides is that the desire to unify forces brought people to think about adding in an extra dimension, or brought people to think that an extra dimension might actually exist. So let's talk about unification of the forces, because today we still kind of have the same feeling. The first time the 2 forces were unified were in the mid-1800s, with James Clerk Maxwell unified the electric and magnetic forces into a single force. We're all very well familiar with electricity and magnetism, but there are actually 2 different manifestations of a single force called electromagnetism, And we've known that for about 150 years now. There's this great story about Maxwell, in fact. Apparently, he was having some trouble getting funding for his lab because he was just doing basic science at the time. And the Queen's treasurer would come and say, "Why should we fund you?" And his story is, "Well, I can't tell you why today, but I promise you in the future you will tax people on it." I don't know if we can really say the same thing today, but we do still aspire to unify all of the known forces today. And let me show you just schematically here in this little picture in the lower right-hand corner how we think that can happen. And that is the strength of a force. So that is like how much an object can feel a force, okay, changes with energy, okay? So what I mean by when it changes with energy is you measure an interaction of, say, two apples. You measure the gravitational interaction between them at two different energies. You would get a different strength of that interaction. Some forces, like this red force here, this is as energy increases. Energy increases as you go more towards the right. Some forces can decrease in strength as energy increases. Some forces can increase their strength and become stronger as you go up to higher energies. And our hope is that someday they will all unify at some single point. Yeah. Yeah, the energy of how you measure an interaction. I'll show you in a little bit that's the same. I'm trying to think of an example where you would measure the same thing at two different energies. Well, I guess you could have two electrons colliding here in the accelerator, which is a very high energy, or you can have two electrons colliding in as they circle around the nucleus of an atom, which is a very much lower energy than what we do here. So that's what I mean by two different energies. Did that make sense? Yeah, you can think of it that way, yeah. Okay, and this is a little chart of what we hope will happen. Now, we know about four forces, okay? Here's gravity here down at the bottom, and here's Maxwell's electromagnetic force, and we know about two more forces. There's a weak nuclear force. This guy is responsible for radioactivity. It's also responsible for making the sun shine. It's a pretty important force for us. And the strong nuclear force, this is the guy that binds the constituents together inside of a proton or a neutron. Okay? It's named strong because it's strong. We are currently probing energies, okay? Energies of interactions, I guess when particles collide, at this particular scale here. And you may notice that it looks like something really exciting has happened at this big red star, because these two lines, the electromagnetic force and the weak force, have come together, and then at higher energies, increasing energy going to the right, they unify into one. I should also point out, it's not only increasing energy to the right, but it's also earlier times in the universe to the right, okay? So higher energies means we're probing earlier times in the universe. So something exciting has happened, and that is what is shown down here, where these data points are actual data. You see, as a function of energy, at a particular energy, here the electromagnetic force and the weak force have unified into a single force. This is something that we've observed in experiment. It's truly exciting. We've called it the electroweak force. We like to make names shorter. And the thing that I want to point out is that it's happened right at the energies that we're currently probing now in high-energy accelerators. So there's two big questions that we have. When does gravity come along and unify? Well, we want to know when the strong force comes along and unifies as well. I mean, we're so excited having unified two of these guys that now we're really anxious. We want to get the other two guys on board here. Okay? And one big one is, when does gravity unify? And the other one is, what breaks this electroweak force? Okay? If you're at high energies or early times in the universe, this is a single force. and then some down at some later time or lower energy, this force suddenly splits up into two different distinct forces. Why? We really don't know. I mean, we've got a lot of theories, but we need to do the experiments to find out what really happens there. And extra dimensions play a big role in answering both of these questions. Okay, this is one of the main motivations for the existence of extra dimensions, is that it might tell us what's going on with gravity, and they might tell us what's breaking this electroweak force, why this force decides to split up into two. So now we need to say a couple words about a particular theory of gravity called string theory. This is where string theory is a very popular theory, and you might have heard about it in the press. It gets a lot of attention. People are very excited about it. That's why it gets a lot of attention. And here people think that all elementary particles of nature aren't actually particles, but are actually tiny, teeny tiny vibrations of a loop of string. Okay, so instead of an electron, which I've drawn here, being a point particle at very, very tiny distances, which is 18 orders of magnitude smaller than we can currently probe in experiments, okay, we think that it might not be a point particle, but a loop of string. And that this loop of string vibrates, and that's what's giving the electron its mass and all of its properties. So string theory does something that sounds very fancy. It reconciles quantum mechanics with gravity. All you need to know here is that there's a huge, huge problem with trying to introduce gravity in with quantum mechanics, and it doesn't work unless you use string theory. Okay? But mainly, it can reproduce all known elementary particles if, it can only do these two things if a certain condition exists, and that condition is that there are extra dimensions of space. So string theory predicts extra dimensions of space. Put it in big letters. Not only does it predict extra dimensions of space, but it tells us how many there should be. Maybe, kind of, okay? 6 or 7, can't make up its mind. You ask a string theorist and it says, well, it depends on how you look at it. But at least it's not 2 or 10, and it's pretty definite here. It's either 6 or 7 extra dimensions of space. So there's one more radical new idea, because string theory happens at very, very tiny distances, but there's a radical new idea that these extra dimensions could be huge. Okay? And it's trying to answer a couple of questions. One is, why is the strength of gravity 100 billion, 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 billion times weaker than the other forces? Now this may not, I don't know, it might sound a bit strange to you all, because you think of gravity as a pretty strong force, right? I mean, that's why you're rooted to your chair. It's why I'm rooted to this floor. It's a pretty strong force for us. But the other forces are even stronger. In fact, they're 100 billion, 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 billion times stronger. Okay? Gravity's weak. Why? Okay? Perhaps gravity is actually strong, these new ideas say, but it only appears to be weak to us because it's moving out through a much bigger, higher dimensional space-time. Our 3 + 1 dimensions is only a very small sliver, a very tiny fraction of the full volume of the universe that gravity can move around in. Okay? It spreads out and spends very little time with us, and that's why it appears weak. We only get to see a small part of it. Given this hypothesis, extra dimensions can be big. In fact, sub-millimeter. This is 100 microns. And for those of you not used to what a micron is, it's basically the width of a human hair. So extra dimensions in this theory could be 100 times wider than the human hair. It's huge. Okay? At distances of this size, that could be responsible for breaking the electroweak force. It's just at the right place. So these are the guys who are responsible for all these wild new ideas. We've got Savas here at Stanford, and everybody else is on the East Coast. 2 from Harvard, 1 from New York University, one from Johns Hopkins. And if any of these ideas are right, then we'll see wine glasses and beer mugs with their faces on it in the future too. In fact, NEMA has already started to corner the market. If you look very closely at this coffee cup he's holding, he's got a picture of himself on it already. Okay, so extra dimensions are actually good for a lot of things. I've just told you about a couple of them, about gravity, string theory, and this electroweak force. So those are the first three on this list, but there's a whole rest of the list as well. And you may or may not have heard of some of the things on this list, and it doesn't matter whether or not you have. The important thing is to say that extra dimensions can answer a lot of the questions that we have before us today. Okay, how do we visualize extra dimensions? This is very, oops, this is, oh, I got it onto a thing. I'm a theorist, I don't know how to use equipment. I won't say Lance is a theorist as well, but at least it's his thing. And I've got this little doohickey in the corner now, too. Okay. We'll get there. Yeah. Okay. We tried to use technology. Okay, so extra dimensions are difficult to visualize, and I'm going to try and explain it to you several different ways. One picture, which is popular with a lot of folks, is to project shadows of higher dimensional objects on the smaller dimensional spaces. And this one here is a famous example, and it's one that we can all go home and try, actually, where you have a flat sheet of paper, something two-dimensional plane, okay? And then you have a cube. Rotate the cube over this paper, throw a light behind it, watch the shadow that the cube makes on the paper. This is something that Carl Sagan did in his special that he televised in the 80s, I guess it was. And what it is, if you were confined to living in this two-dimensional plane, which looks like a table or a piece of paper here, you would imagine a three-dimensional shape by the shadow that it would cast on your plane as it rotated above you. Well, we can do the same, okay? This is the three-dimensional shadow of a rotating four-dimensional hypercube. So it's rotating, so that's why there's four of these cubes. The two different colors is supposed to convey the 3D picture of the thing. And now I've got a question for you. Does this make sense to you? Does this do anything for you? It doesn't for me. Not at all, okay? I've just never gotten this. So let's try another way of visualizing extra dimensions. And let's think of extra dimensions as being small, too small for us to observe. So they're curled up, compact. By compact, I mean very small and finite in size. And let's look at this following picture. Here we've got a tightrope walker who, for some inexplicable reason, is walking along the suspension cables on the Golden Gate Bridge. Now for this guy, there's only one dimension he can follow. He can go forward or he can go backward. He tries to step off to the side, he's in serious trouble. So to him, to his world, there's only one dimension that he can see. He can't see any other dimensions. He can see forward and he can see backward. That's all he can see. What about these ants? Okay? These ants are small, and they can see two dimensions. They can crawl back and forth, just like the tightrope walker can, or they can crawl around the suspension cable. Why can they crawl around the cable? It's not because they've got suction cups on their feet or anything. It's because they're smaller than the size of the circle, of the radius of the cable here. Because they're smaller than this dimension, they can see it. Our tightrope walker is quite a bit bigger than the width of this cable, so he can't see it. It's not useful for him, but it is useful for the ants. So in this picture, every point in space-time has curled up extra dimensions associated with it. Just like in this picture, every point along the back and forth direction of this cable has got a circle associated with it. So for one extra dimension, you have this circle associated with every point in space-time. For two extra dimensions, you would have a sphere associated with every point in space-time. For 6 extra dimensions, which is what superstring theory wants, you have these potato-like things at every point in space-time. And these potato-like things have a fancy name called the Calabi-Yau space. Okay? So if this picture is correct, then every point in this room has some number of extra dimensions curled up and attached to it, just like the ants on the tightrope. Okay, yet another picture, another way to visualize extra dimensions. This is something that's only 10 years old now, and it's called the brain world scenario. We like funny names, okay? Brain world scenario. And the idea here is that we are trapped on a 3-dimensional space called a brain or a membrane, and we can't get off of that, okay? So here's a picture of that. We're here, the Earth, and we're trapped on this membrane. It's drawn in 2 dimensions because it's hard to get the other dimensions to go around it if you draw it in 3 dimensions. So even though it's drawn in 2 dimensions, we mean it to be 3-dimensional. So you've got the Earth trapped on this membrane, and there's a whole higher dimensional space all around it. We can't see it because we're stuck on this brain. Can't move off of it, can't see anything off of it. Okay? Gravity, in these particular theories, however, can move all around this higher dimensional space. It can zap through us, it can be moving up here, it can move around the full volume of the universe, but we can't. We're stuck on this membrane. In these theories, and there's many, many of them, actually many different variations of them, these extra dimensions can either be very small or very large, either one. Each one has a different prediction on how you would see their existence in experiment. Yeah?
Wouldn't the universe all be on the one brain?
Yeah. It's really difficult to draw. So if you're not getting that from the picture.
I meant the gravity may pass through that brain, but be in other dimensions before it does.
Right. That's exactly right. You understood perfectly. Yeah.
So you said earlier that gravity appears weak because it propagates through all of these extra dimensions.
This is the
Does
picture for that.
Does that imply
Yeah.
that, for instance, electromagnetism stays in our 4-dimensional space-time?
That's right. But why? When these theories first came out, it's what people assumed. Okay? Now, to be perfectly honest, we have new models where we stick all sorts of stuff, including electromagnetism, out in the extra dimensions. Okay? Let me just say that there is a mechanism within string theory, okay, for which things like electromagnetism and protons and neutrons and stuff are stuck to a brain, and gravity is free to move everywhere. There's a particular way you can realize that within string theory. And so that's why people tend to like to think about gravity moving everywhere. Okay. So what about these particles or these forces that are moving about in the extra dimensions? Well, here's Einstein, the real picture of Einstein with what he really wrote on the blackboard, with his famous formula that we all know, mass equals energy. However, this formula is incomplete. This is for a particle at rest. What if a particle is moving? Okay, what if you have a fly that's flying across this room? It has a mass, and it has a momentum or a kinetic energy associated with it, right? That's not in this formula. So we have to modify it a little bit to include the motion of a particle. And so that's what I have down here in this very complicated looking thing in the box. So this box has the E. I've had to square everything, okay? But this box has the E, and it has the mc squared. And then it has these other terms that are associated with the momentum of our fly, okay? And we have 3 of these terms because there are 3 spatial directions that the fly is moving in. Okay? So the real expression is E plus a whole bunch of terms for the momentum, 1 for each spatial direction, plus the mass of the fly. Now, what about extra dimensions? So now let's imagine a particle moving in a single extra dimension. Let's keep it easy. Let's just think about 1 dimension and not those potatoes. So the single extra dimension is a circle of size r. Okay, now you're going to ask, why is a circle, which we all know has 2 dimensions, you describe it by x squared plus y squared, considered 1 extra dimension? Okay? Because the radius of the thing is fixed. That's not a variable. Okay? The only variable, the only independent way an object can move is if it goes around the circle. It's like the ant. The ant is stuck to the outside of this cable. So a particle moving in this extra dimension only can move around in this angular space. So if you like, those of you who know polar coordinates, theta is the only other variable. Okay? The radius isn't a variable. So particle is stuck to move around this circle. It's moving. It has momentum, just like our fly flying through the auditorium. It's moving. It has momentum. And quantum mechanics says that this momentum comes in steps. We're in Silicon Valley, so some of you might have had quantum mechanics. First thing you learn in quantum mechanics is something called particle in a box. And what that tells you is that if you have a particle and it's moving in a confined space, momentum comes in steps. It can't have any old value. It can only have particular certain values. Okay? The fly moving through this room can have any value of momentum. If it was moving in a very tiny thing, it can't. Okay? And not only does it have to come in steps, but the steps have a particular size. Quantum mechanics is very picky. Okay? It comes in particular sizes, has to be a multiple of 1 over the radius. So the momentum, this extra momentum associated with our particle moving around the circle, or with our ant walking around the radius of this suspension cable, is given by 1 over the radius in multiples of this 1 over the radius. So we write that as n over r, where n can take on any integer value. It means 0, 1, 2, 3, no fractions. Okay? So back to our equation. For this particle, which for now I'm labeling Kaluza-Klein, okay, for this particle moving around in the extra dimension, here's our energy formula for it. Here's the energy we had before. Here's the mc squared. Here's its momenta in the 3 directions we know. And here's its momenta in the extra dimension. Now compare this to what this equation looks like from the 4-dimensional perspective. For 4 dimensions, you've got momenta in the 3 spatial directions we know, plus mass. So anything else you add to this equation here is going to look like a mass to us, because we can't see the extra dimension. So for us, it looks like a mass. Okay? Yeah?
The Pythagorean nature of this equation you have up here would seem to imply to me that the mass is also orthogonal to your dimensions, because of, because you've got, if you have 3 dimensions, you'd have the square plus the square plus the square, right? But why is mc squared squared and added like that?
Okay.
Is mass orthogonal to the spatial dimension?
Not really. Mass is a constant. It's a property. I have a mass. You have a mass. This bottle of water has a mass associated with it. So it's a constant. Okay? It is true that we're summing, if you like, the 3 different, the momenta associated with the 3 different coordinates. Okay? And for a triangle, that has to equal whatever, the area of the triangle or whatever. And for here, it has to equal the energy and the mass. Okay, so if you want to think of it that way, think of it that way. But the mass isn't orthogonal. It's not a direction or a dimension. It's a constant. It's a property of an object.
Is it scalar?
Yeah. Okay. So we've established that this extra piece to us, sitting in 4 dimensions, looks like a particle with a mass given with what's underneath the brackets here. This is the mass of this extra particle. It's real mass, okay, plus its extra momentum in the extra dimensions. Now recalling that this extra momenta comes in steps of 1 over the radius of the extra dimension, what this builds up for the different step values, okay, is an entire tower of massive particles. Okay? So for the first step, n equals 1, you have a particle with this particular mass. For the second step of n equals 2, you have a second particle of this particular mass. Third step, third mass, and so forth. Okay? So this builds up a tower of massive particles, and we name that after Kaluza and Klein, because they're the first ones that did it. Now, if you have a small radius, so you have a small dimension, this gives very well separated Kaluza-Klein particles, right? Because it's 1 over the radius. If that's small, then this is a big number. If it's a very large radius, like some of these new theories, okay, that gives very finely separated Kaluza-Klein particles. And you see that you stack up a tower of different particles much more quickly. So this is what we're looking for in experiment. This is the key right here. We're looking for these particles. And the person who's really awake and thinking after listening to me for so long has realized that we can learn something about the size of the extra dimension by measuring the mass of these particles. If they've got a big mass, and we've measured the first 2 or 3 of them, and we know the separation, then we know R. Okay, so back to paintings. This is a local Bay Area artist, lives in the North Bay, and she's painted a series of paintings for us. And this one is for Kaluza-Klein particles, and I'm particularly captured by her name because we have particles named mesons. I think she was destined to paint for physics scenarios. Okay, but as we just said, the observation of this Kaluza-Klein tower of particles is what shows us that there's an extra dimension. It shows us that a particle is traversing a confined space. Measurement of the properties of these particles tell us the properties of the space. We've already sort of seen how you can get the size of the extra dimension by measuring many different particles, or observing many different particles in this tower. Once we observe these particles, there's a whole bunch of things we're going to want to know. After we get over initial excitement of having found extra dimensions, there's a whole bunch of things we're going to want to know. How many dimensions are there? How big are they? What is their shape? What particles feel their presence? Gravity, electromagnetism? Do we live on one of these membrane things? There's also some more practical questions we might have. Like, can we park our cars there? And is that where all the socks go when you do laundry? Yeah. And could we have some extra time dimensions too, because we all need more time? Okay. So in the last 10 minutes, I'm going to explain to you the different ways that we search for extra dimensions. And there's 3 ways. And they're completely separate from each other. So if you phase out during one and then phase back in, don't worry, you haven't lost the whole rest of the lecture. But there's 3 ways we hope to see extra dimensions. One is modification of gravity at short distances. One is looking for these Kaluza-Klein particles up in the sky, astrophysics, cosmological processes. And the other is creating them directly on here on Earth in high-energy accelerators. So I'm going to just say a few words about each of these, show you how we do it and what progress we've made so far. But first of all, you might be thinking, how can we see this thing that's sort of invisible? And I just want to explain to you how we do experiments. And one analogy is to think of footprints. How skilled animal trackers can really learn a lot of information about an animal from their footprints. They can learn what type the animal is, how big the animal was, how fast it was going, if it was injured or not, and all of these without directly observing the animal. We know this is true because we've got information even when the animal is extinct. This is how we gather information on extra dimensions, even if we can't see them directly. So looking for these Kaluza-Klein particles is our indirect way, okay, of looking for extra dimensions. Okay, so for the three techniques, first one, modifications of Newtonian gravity. Well, first of all, we have to know what Newtonian gravity is. Okay? So Newton discovered Newtonian gravity. Here is the expression for his force. The gravitational force is equal to a constant called Newton's constant. This is the force that describes the interaction between two objects. So it's the mass of the two objects. Here in our picture, it's the mass between an apple and Newton's apple tree and the Earth, okay, divided by the square of the distance between the apple and the Earth. And this is the important point here, this is just a constant, is that it goes as 1 over the distance squared. Okay? And it's the distance between the two objects you're concerned about. It's 1 over the distance squared. Newton had a very large effect in our field in many different areas. So not only did he get on the money, but he was knighted. I don't think they knight physicists today. Okay, so what if there's extra dimensions? What happens to this Newtonian gravity? So I'm going to give you an example of 2 extra dimensions. Remember, that's our picture of the sphere at every point in space-time of a particular radius r. So for distances greater than the size of these extra dimensions, so for anything bigger than these 2 green arrows here, you don't really feel the presence of this extra dimension, as we know. Okay? So the gravitational force law hasn't changed. It's still 1 over r squared. But for distances inside the extra dimension, once you're smaller than the extra dimension, then the force law changes. It's no longer 1 over r squared. It's 1 over r to the 4th. So it's the power, 4 times the power of the distance, okay, between 2 objects. This is measurable. This is huge. This is a very big deviation if you can measure small distances. Okay, so this is the apparatus that we use. There's 3 ongoing experiments, one in Colorado, one in Washington, and one here at Stanford. The apparatus is small. We lovingly call it a tabletop experiment. It means it's only about a foot tall. That's pretty rare for our field to have something that small. And it's this really cool thing, and I'm a theorist, but let me try. It's 2 torsion wheels. So there's one on the top and one on the bottom. This top torsion wheel is attached to this thing, and it's a pendulum. Here's this invisible string, so it's hanging up from the sky. And this bottom one is the attraction wheel, and both of these wheels have holes cut out of them at very well calculated spots. And the bottom wheel turns back and forth, and it creates a force on this top guy, and it starts to turn back and forth. And by that, they actually can measure the gravitational interaction between these 2 wheels. How well they can do is determined by the actual mechanics of the thing, okay? And the current best limit on extra dimensions is now 1/10 of a millimeter, or 160 microns. Remember, this is 160 times the average width of a human hair. This is just above the prediction of this new theory with the guy who's got his face on the coffee cup. Did I do the zeros wrong? Oh. I did that wrong, didn't I? Yes, I did. Okay. Just cross off the meters here, a centi, and think of it as meters. Yeah. Okay. Sorry about that. I think I've done that later in the talk as well. Yeah. Meters. Right. Just cross off the centi. Sorry about that. Okay. This one is correct. You can't trust theorist calculations. We're just no good at it. Okay, so modifications of Newtonian's gravity. Remember Klein's prediction. This was his prediction with the some 20 some odd zeros in front of the centimeters. And now a micron is here. Okay, so the present limit would be here. Okay, would be here at submillimeter. Okay, so the point is that the constraint is not very small compared to Klein's very small prediction for the size of extra dimensions. So we really have pretty poor limits using this technique, and it's about as good as this technique can do. They think they can do about a factor of 10 better, factor of 2 better, but that's it. The other thing to note is that because the limit is so poor, extra dimensions really could be big. These theories that have them at the sub-millimeter level or 100 micron level really could be right. Okay, method number 2, finding extra dimensions in the stars. This is a picture of a supernova that happened 200,000 years ago, and it's in the small Magellanic Cloud. So what is a supernova? Basically, when stars burn, they use fuel. When they burn up their fuel, they go through a lot of different things, but the end result is that they explode. Okay? And this is called a supernova. What happens, you don't want to be near one when it goes off, I can tell you that. And what happens is that it expels particles and releases energy when a star explodes. If there are extra dimensions, and if there are Kaluza-Klein particles, then these would be ejected into the extra dimensions as well. Okay? So the supernova, along with spewing out all the ordinary particles, would also spew out these Kaluza-Klein particles, and they would zip off into the extra dimensions. So this would release more energy from a supernova than we currently know about. We actually have calculations of supernova explosion. There's like a standard model of supernova explosion. And this would be in conflict with it if the extra dimensions were too big. Okay? And this is the limit, and I know this one is right in centimeters because I just did this today. Okay? So for 2 extra dimensions, this sets the constraint on the size of the extra dimension to be quite small. However, there's something to keep in mind. This is predicated on our standard model of supernova explosions. We've never really been next to one to study one when one's happened, right? They've always been far away, long, long ago, and it has many assumptions built into it. This isn't the same as studying it in a laboratory. It's also only for 2 extra dimensions. If there's more extra dimensions, the constraint gets much worse. Okay, last technique, the colliders. What's a collider? A collider is actually a powerful microscope. They make high-energy particle beams, and that lets us see small things. That's because energy is related to 1 over the distance. So the higher in energy you go, the smaller distances you can probe. High energy, small distance. So something like an atom, as seen by a low-energy beam, you can't resolve the particles inside of an atom if the beams are of too low of an energy. If you have a high enough energy beam, you can see the electrons and the nucleons and all of that inside the atom. There are also time machines because higher energies correspond to earlier times in the universe. So they make particles that were last seen in the earliest moments of the creation of the universe. And you have 2 beams of particles. You accelerate them up to very high energies. They collide, they annihilate, and what you get is a big burst of energy. Energy equals mass, right? You get a big burst of energy, and then you create a bunch of new particles that we don't normally see in our everyday world. So there's a new collider that's coming online. It's called the Large Hadron Collider. It's going to collide protons on protons. It's going to explore energy regions up to a factor of 10 over what we can do today. It begins operation in only 431 days. It's in Geneva, Switzerland. This is a picture of it. It's 27 kilometers in circumference. That's close to like 20 miles. Here's Lake Geneva. Here's the Alps. Here's the town of Geneva. This is an actual magnet inside the tunnel. Okay, so the particles zip down a beam line in the middle of this magnet and get accelerated. We're all really terribly excited to play with our new toy. There's 2 major detectors that are being constructed to observe the particle collisions in this new accelerator. SLAC is planning to join one of the collaborations. Collaboration we hope to join is ATLAS. There are 1,500 scientists working on this collaboration and growing. The detector weighs 7,000 tons. Just to put that in perspective, that is 20 Boeing 747 airplanes. The detector is so big that they actually claim it can float because it's not very dense. Okay, so even though it weighs so much, it's big enough it's not dense, and the claim is it can float. Here's a picture of the detector in the collision hall, and there's a little guy here in the red circles. That gives you an idea of the size. There's a webcam, and it's updated every 30 minutes, so you can see how progress is coming. And this is the picture of the detector as of this morning. It doesn't change very much from 30 minutes to 30 minutes, I'd have to say. There's another collider that's being proposed called the International Linear Collider. This is just a longer version of what we have here at SLAC. So if built, it will collide electrons and positrons. It'll be 20 miles long. It'll have the same energies as the LHC. And we'd really like to have it here in the US because we don't want to have to go to Europe to do all of our science. So how do we find extra dimensions at these machines, and what sort of range can they look into? Okay, I've just got 2 scenarios to go through here. One is the case where extra dimensions are flat. I'm going to do the brane world thing. We're stuck on a brane, can't move. Gravity moves all around us in the extra dimensions in the universe. So the Kaluza-Klein particles we're interested in are those particles associated with gravity called gravitons. Our 2 beams in our collider collide. It produces a spew of stuff, and it produces the graviton, which escapes into the other dimension. The spew of stuff is needed to balance the graviton escaping. Because this graviton particle goes to the other dimension, we don't see it. So this is an experiment where we don't see the particle that we produce. Very tricky. How do we look for particles we can't see? Well, we know the total energy of the collision. We put that in. We did that. Okay? We can measure the energy of the stuff that we do see. If they don't match, then that's something called missing energy. We've missed something. Okay? So we search for missing energy. And this is our way of looking at it, where this is the energy deposited into the detector from the spew of stuff that we saw. And then there's nothing else. There's something missing. Okay? So this is a simulation of what graviton production would look like. If we saw this type of thing, we'd be really excited. Okay, I'm going to give you another scenario. This is number 2. This is a different type of brane world scenario. The dimensions here are curved instead of being flat. Again, our Kaluza-Klein particles are gravitons because they're moving throughout the full universe. We're producing them in a lab. Because the extra dimensions are curved, they have different properties. They don't spew out into the extra space. They decay here in the detector. And they decay to ordinary particles that we see. This is what it would look like to us, where this is number of particles produced versus energy of the machine. These bumps that you see correspond to these different states. Okay? So as you increase the energy, each time you see one of these bumps, you've produced one of these states. You measure the distance in energy between these bumps. You know the distance between these states. You know the size of the extra dimension. Cool. Okay, these searches will, if they don't discover extra dimensions, set a limit of this centimeters for 2 extra dimensions and a much, much stronger one for 6 extra dimensions. Limits depend on how many extra dimensions there are. This is still much bigger than Klein's prediction of this many zeros before the 1 in the centimeter. But if our ideas are correct, and these extra dimensions have something to do with breaking that electroweak force, this is exactly where they should be. Okay, we should see them in this range if they're connected to that force. Okay, I had one more example for you, which I think I'll skip, and I'll just finish with my new toy that I found on the web. And from the words from Einstein himself, extra dimensions would profoundly change the way we view the universe, and we need to search for them and discover whether or not they're actually there.
Yeah, that was great. We have time for some questions. I have one over here.
There's something called the Pioneer, the spacecraft Pioneer anomaly. And it's also been seen, I think, in one of the 2 Voyagers. Could you tie this in with?
Yeah, this is a very famous thing that has us all puzzled. And there's data from a particular year, and I think it's like 1989 onwards. There was a flyby of, it was either Jupiter or Saturn, from this spacecraft called Pioneer. And when it did a flyby of one of the big gaseous planets, its rate of acceleration changed. And it's been constant since then. And it changed compared to what we calculated it to be from Einsteinian gravity. That's the point. Okay? So its rate of acceleration is different than what we thought it should be if Einstein's theory of general relativity was correct. So lots of things happen in when you do experiments, and you have to do more than one experiment to confirm a signal that has as profound consequences as something that this one does. And apparently there's data from other satellites that the JPL, I think, is leading this now, right? That they're trying to go back and look at this other data and see if it's actually been seen in other satellites or not. And if it's correct, that shows that there is some sort of small correction to gravity that we don't know about yet, I would say. Yeah. Could be.
Other questions? There's one way back there. Yeah, you.
In one of your slides, you're showing the at different energies, different forces convert, unify. And I believe at lower energy, there's the electromagnetic and the weak. You're showing that
Right.
the star.
Right.
And at higher energy, there's gravity and so on and so forth. I was wondering why is that, like the ordering of that? Why couldn't, for example,
It's because of what we've been able to explore with experiments so far, right? We basically started ground zero, zero energy, and we've explored up to a particular energy, and we've seen those 2 forces converge, and we just haven't explored higher energies. One of the theories that we have is that the other forces come in and unify at greatly higher energies. Extra dimensions can tell us that they might come and unify at energies that these 2 new colliders would be able to see them. And we just have to explore those energies to see when it happens, if it happens.
There's a question in the front row, or?
Oh, yeah. Well, how would the discovery of like different dimensions, A, our understanding of the size of the world, and B, just how our world works in general? Like, what's the benefit of discovering?
I think it would basically change everything, the way we think about the universe. I mean, this is a discovery that would change how the person on the street thinks about the universe, because we've discovered a whole new space.
Yeah. But other than how you think about it, would it change anything to you other
I'm sure that it will within time. It's the famous thing is Maxwell with the Queen's treasurer, right? How is this going to be helpful to us? I don't know, ma'am, but you'll tax on it. I'm sure with technology, we'll learn how to utilize these extra dimensions. And just until then, just the excitement of knowing about them and what they're like, and just knowing more about our universe that we didn't know before is just, I don't know, it's the kind of discovery that would capture the average person on the street. Because our universe would mean that our universe is different than how we've pictured it.
Question over here.
What does it mean that different kinds of forces are converge or are unified? What does that mean?
Well, it means that a single force manifests the qualities of all the different ones. And you can describe it in just one, you can describe it in terms of one entity, okay? You can use all the mathematics and the equations and everything, but you can describe that one force as one thing, but yet it has the characters of all the other forces. Just like electromagnetic waves, they've got electricity and magnetism associated with them because it's a unified force. Whereas electricity and magnetism, I mean, you can really think about them as two separate things. But the unified theory describes both of those two separate things in just one set of equations. It describes it in just one way.
Question over here.
So that's a question for currently has a very short range. When it is combined with high energy, does that mean that it acquires an infinite range? Or does it
No, because remember, high energy means tiny distances.
so
Yeah.
magnetic force is short range. Something else I was puzzling over was this system currently being because
It's spending all of its time elsewhere and not with us. Yeah. Oh, right, yeah. Mm-hmm. Space-time had these extra dimensions curled up with it, and gravity can go in those little extra tiny balls. Because you add up the number of those little tiny balls, and once you sum all of them up, it gets to be a big number. Yeah, it gets to be a very big number.
So I think it's now time to thank JoAnne again, and there's plenty of opportunities to ask more questions in private afterwards. Let's give JoAnne a big hand for putting everything together.